All right, good morning. We're going to continue on with alcohols and phenols. We started talking about acids and bases and the acidity of phenols, and we were last comparing and looking at cyclohexanol versus phenol. Where we ended. Which one is the stronger acid?
The bottom
Which
one.
one is the stronger acid?
The bottom one because it's resonance stabilized.
Okay, the bottom one because its conjugate base is resonance stabilized, so the pKa of this is about 10, whereas this one is probably somewhere between 16 to 18. Okay, so there's proton and conjugate base is resonance stabilized through the aromatic ring. All right, so this is also, even though this is resonance stabilized, this is a weaker base, this is a weaker nucleophile as well because of the delocalized charge on the alkoxide. Okay, so that's kind of a new word for you, alkoxide. Okay, alkoxide would be like sodium ethoxide, potassium T-butoxide. These are in general called alkoxides. Okay, all right. Let's take a look. Choice of base. Choice of base. Bless you. Metal, just a metal ion. Yeah. Which one would be the most appropriate base to use and why? One would be the most appropriate base to use and why?
Bottom one.
Okay, so we have N-butyl lithium at the bottom to make butane.
Because the conjugate acid, the high pKa is the stable one, right?
Yep.
The stable conjugate acid, so it's a weak acid, it's gonna be a stronger base.
Okay, so which one is the strongest base?
One with the highest pKa with conjugate acid.
That's right. Okay, so this must be the highest or the strongest base, but you also have to consider what else? The other protons that are on here, right? Would it work? Would it work? Probably. Okay, it would probably work. I think it's a little too strong though. Okay, Now, especially if you had other functional groups on this that it might act upon, okay? So typically what you want to do is choose a base that is a few units higher than this one, but not too high, okay? So sodium hydride would actually be a little bit better to use for this. pKa of this one is, again, 16 to 18, somewhere in here, and 25 is a little higher, a few units higher, okay? So, how does sodium hydride work? How does it work? What does it produce? It produces hydrogen gas as the conjugate acid, but what's the basic species? What's the basic species? Sodium has what charge on it, Hunter? What charge does sodium get?
It's the hydrogen.
Look on the periodic table. Sodium's in group 1.
The hydrogen will have the negative charge.
+1.
Hold on, Hunter. What's the charge going to be on sodium?
It'd be +1.
+1. Okay, so hydrogen must be to balance it out.
Yeah, just a negative.
A -1, that's right, okay? And it's something that you're not that used to, okay? You're not used to seeing hydrogen with a negative charge, but it's very reactive. So, H- is hydride, and you just deprotonate that, break the bond, kick the electrons off onto the oxygen, and then that gives you the sodium alkoxide version of that molecule, okay? Sodium hydride is a white powder, okay? Actually, I take that back, it's more gray. If it's typically white, it's actually reacted with moisture and made more sodium hydroxide, okay? That's kind of how you can tell it's going bad, is it starts going white. But it's a gray powder, and it's actually really pretty hygroscopic. You can't use sodium hydride in a water environment, in an aqueous environment. So if you are doing this reaction, you're probably going to do it neat. That's a liquid, and you're not going to probably put that into solvent. You're just going to do it neat, and then throw in the reagent at a low temperature. So you'd probably cool this down with a little ice water, and then you'd throw this powder in and put it in slowly, okay? What are you going to see as you start putting that powder in?
Bubbles.
Bubbles, that's right. And you're going to start seeing the hydrogen gas come out of that reaction. Yep. And you typically use this reagent in excess, okay? So you typically use it like up to like 1.5, maybe 2 equivalents. 2 equivalents seems a bit much, especially if it's a good bag of the reagent. But when you finish this reaction, what do you think you quench it with? What would you quench it with if you had excess reagent left over? Plus, if you want to use this, right, as the reagent or as the O-, if you quench it, you're just going to go back to here, right? Okay? So this would be used as some kind of a nucleophile. So you'd end up throwing in an electrophile once you form this, and then the electrophile reacts with this, and then you have to quench the reaction. What do you think you might quench it with? What do you think? It's a negative charge, water. Yeah? Just cold water, ice cold water, and you just start putting it in very gently and easily, and then it just starts liberating more hydrogen gas. Okay? I think I told you a story in the lab about a friend of mine who had an empty bag of that, and she was quenching the bag to throw it away in the trash so that it wouldn't generate hydrogen gas and catch on fire in the trash. And she was quenching it with 70% isopropanol, and she was putting that in there, and it generated the hydrogen gas too fast, and she knocked it over. It ignited the hydrogen gas, she put it in there too fast, and then it caught another bottle of solvent on fire and made a big fire in the lab, okay? And she just did it too fast. So you have to be very careful when you're working with these types of reagents. Does anybody have any questions on deprotonating alcohols? I'm gonna add one more thing in here. Formation of alcohols. We've already gone through this, but it's a good review. How can you form alcohols? How can you form alcohols?
Would you mix good electrophiles in water? Would that be one way?
No?
Like oxymerate, mercuration, demercuration?
Okay, so oxymercuration, demercuration would not go here.
Yeah.
Okay.
Oxidation of alkanes.
Okay, so oxymercuration, demercuration. Okay, is going to put it where? Here, okay, which is the Markovnikov or anti-Markovnikov addition? That's the Markovnikov addition, so you need to go back and review that, okay? What about this one? That's anti-Markovnikov. There's something before that. That's the second step of that one. Hydroboration, oxidation. Yep. So, hydroboration, oxidation. There's another one. There's another one. Anybody remember what it is? It will also do this. Will also do this. This one is acid catalyzed hydration. Dilute sulfuric acid, water. Acid catalyzed hydration. These are all review, okay? You need to review all these. You will see those again.
Do we have to are you gonna test some on the
Maybe. This is all cumulative. Remember, by the time you get to the final, right, you will need to remember Samokin 1, Asbaf, right? Yeah.
I thought
think
you
you
said
said,
there weren't
yeah.
gonna be any like the old mechanisms.
I didn't say anything about mechanisms.
I asked you if there would be anything from organic one on the midterm, and you said no.
Okay. This pertains to our chapter, okay? Leading up to this, right? Leading up to this, I did promise you that there would be nothing on the midterm from organic
But is
one.
it just gonna be those 3 mechanisms?
No mechanisms, I already said, no mechanisms, okay? Just synthesis, And I want you to know your reagents, okay? I want you to know your reagents. Okay. Let's talk about redox. Let's talk about some reducing agents. Here's one that you haven't seen before. Sodium cyanoborohydride. This one will not be found in this chapter. This one is one of the most mildest reducing agents. This one is mild, and it's used for reductive aminations. Reductive aminations change ketones into amines. Ketones and aldehydes, actually. It'll change ketones and aldehydes into amines. You have to have some type of a nitrogen nucleophile in order to do that, and then the oxygen from the ketone or the aldehyde is lost as water, and it kicks it out. Okay, so that's one of the more milder ones. This one you've already used in the lab. This is sodium borohydride. Stronger reducing agent than sodium cyanoborohydride, and reducing ketones and aldehydes. Next is lithium aluminum hydride, or LAH. And this is the strongest, or at least one of the strongest reducing agents that you guys will see. Sodium borohydride, what did we use it for?
Reduction of vanillin.
The reduction of vanillin. What did you reduce on vanillin?
The alcohol.
No? You did not reduce the alcohol.
Aldehyde.
The aldehyde, yeah.
You reduced the aldehyde to
Alcohol.
an alcohol. Okay, you reduce the aldehyde to the alcohol. Did anyone in here use solvent that had water in it? Anyone? Did anyone use solvent that had some water in it? No?
I had some NaOH.
Okay, did that have water in it?
Yeah.
Yeah.
Yes, it did.
Oh, yeah.
Yeah, it absolutely did. So sodium borohydride can be used in the presence of water. Lithium aluminum hydride cannot. Okay, cannot use aqueous solvents with LAH. It is more like the sodium hydride in terms of reactivity. You would just end up with a bunch of hydrogen gas, and that's about it. Okay, you're going to quench your reagent when you use lithium aluminum hydride. So lithium aluminum hydride, you have to use other like polar protic solvents, like ether or THF, things like that. All right?
Question.
Yep.
Yeah, sodium borohydride, could that be used to reduce a carboxylic acid to have another alcohol group, or can you not really do that with carboxylic acids?
We're going to talk about that. Yep, we're going to talk about that. So, when you reduce an alcohol using some of these reagents, you can get some really nice chemoselectivity. So let's talk about some chemoselectivity. Last semester you looked at hydrogenation conditions. Hydrogenation is hydrogen with some type of precious metal, whether it's platinum, palladium, iridium, rhodium, those ones that are right there in the middle of the D block, and high pressure. These types of conditions are really not that advantageous and not that good for reducing aldehydes and ketones, carboxylic acids, but they can be used if necessary. The only problem with this is this reaction is not chemoselective. What did you notice happened?
Both the alkene and the ketone got protonated.
That's right, both the alkene and the ketone were reduced, and therefore it's not chemoselective, okay? Using sodium borohydride or LAH, you get chemoselectivity. Don't reduce the double bond. That's actually what's really nice about these reagents. When we start looking at other chemoselective reagents, we realize we've got some really nice synthetic tools to use in the lab in the presence of other complex molecules that have alkenes and other functional groups that can be sensitive to these types of reducing agents.
What's the plus and minus mean again?
Racemic mixture, because I formed a chiral center, and hydrides have no preference. They will come in one side or the other, okay? And you end up with a racemic mixture as a result of that. Now, there are some stereoselective reductions where they can control which side the hydride comes in on, and then you can get stereoselectivity. And they have these big ligands that are attached to them that block one face versus the other, and there are plenty of those examples out in the literature.
So for it to be chemoselective, does it not do the double bond of the carbonyl? It reduces the double bond of the carbonyl, but not the double bond of the alkene.
Yeah. So it's only working on this functional group and not on this.
So it doesn't work on the alkene.
Yep.
Okay, you keep saying a ligand, is that a ligand? Like, is that what you're saying?
So chemistry, it's pronounced ligand.
But is it the same thing as a ligand?
It is.
Okay.
Yeah, so some biologists pronounce it as ligand, and chemists pronounce it as ligand.
You tell me that every time you say it, I'm like,
Yep.
is that what he's saying?
Yep.
Okay.
I've heard it pronounced both ways, but in the chemistry realm, I've only heard it as ligand. Now, maybe in Europe, maybe they say ligand, okay? I'm not certain. Okay, I'm glad you get a good laugh this morning. All right, so, in the presence of excess reagents, especially LAH is actually more promiscuous than sodium borohydride, okay? I don't know if I should use that word here. Okay. Less selective, how about that? Less selective, less picky, okay? All right. LAH can reduce an ester all the way down to the alcohol. This is essentially, is it a 3 mole or a 2 mole process? Anyway, it's an extensive reduction, okay? You don't get the carboxylic acid as an intermediate. You can't stop it there, okay? So again, the reason why I was saying it's more promiscuous is essentially because you can reduce ketones, you can reduce esters, you can reduce aldehydes, okay? It works on a lot of things, okay? Whereas sodium borohydride, because it is a little more mild, it's actually a little more selective. Let's see if I can find an example for you. Does anybody have any questions?
Whenever we were choosing, this is like a while back, whenever we were choosing the copper base for a reaction, was it basically just choosing a base whose conjugate acid would have a pKa higher than what we started with, but not too much higher? Okay.
Yep.
Alright.
Yep. I mean, you know, there are those instances where maybe you ran out of a reagent and you had to use something stronger. But in those instances, sometimes they will use less than 1 equivalent, so they'll do like 0.9. So you don't have all that excess hanging around in the presence of your molecule to essentially destroy it.
But if your starting material had a pKa of say 18 and you had to choose between a reagent with pKa of 25 or 26, which one would you go with? At that point, does it really matter? Or?
Yeah, at that point it doesn't really matter that much. Yep. Any other questions? That's a good question. I'm really interested in the fact that your book doesn't talk much about the selectivity. We may discuss that a little bit more later down the road. That may be a little too much for this point in our discussion. So, ester, carboxylic acid, it works on both.
Why does it reduce it down to that point and not like 2 alcohols where the carboxylic, or where the carboxyl group becomes an alcohol?
Where you have 2 alcohols here,
Like, yeah.
Yeah.
it's actually not stable. Yep, it's actually not stable.
Why is it not?
That's a good question.
Is it
Why is it not stable?
Is that beyond our scope of organic too?
I'll have to think about it a little bit. Mechanistically, I'll have to think about it a little bit. But I know that it's not stable.
Is it just sheer bulkiness? Is it
No.
even that oxygen? No?
No, it's not. I think it's just the propensity to lose water. It really just wants to lose water. Yep.
Could it be the polymerization?
No. I mean, the only thing I can think of is, again, you're under basic conditions, right? You're under basic conditions. So kicking out a hydroxide under basic conditions should be okay, right? Because you're under basic conditions. So here,
It's too many lone pairs. Plenty oxygen.
no, no, I have a feeling this is how it goes. So,
Are you sure?
Are you sure that's not too many little pairs?
no, here,
Okay.
here, I meant up here.
I thought you were talking about everything.
No. So drop down, kick it off, right? Drop down, kick it off. See, now you've got from the carboxylic now to the aldehyde, see it? And now the hydride coming in, kicking that back up. You see it now? Okay? And then that's what forms the alcohol, right there. Yep. Thanks for the challenge. I think that's the mechanism and how it works. Make sense? Okay? All right, good. I didn't think we'd get this far today, but let's talk about a brand new reaction for you guys. Now, the Grignard reaction.
So what's it now?
Grignard reaction. Looks like Grignard, Grignard. It's a very interesting reaction, but it's very useful, extremely useful. Magnesium can insert between a carbon halogen bond. How interesting is that? Okay. Why do you think this can happen? Why do you think this can happen?
Does it have to do with the charge associated with the magnesium?
It does. It does. What does magnesium like to be?
Positive.
Likes to be a positive what?
2.
Positive 2. Okay? So if it's sitting in between two atoms, right, then its oxidation state should be
Neutral.
what is it here? What is it there? What's its oxidation state?
Plus 2.
The +2 state, right? But magnesium 0 is when it's by itself. Remember? Okay? So it should be mimicking its oxidation state of 2+ here. But what we see is this polarity, right? This dipole that exists between, first of all, between the carbon and the halogen. Okay, there's polarity in this bond. Okay, there's still polarity here. There's still polarity here. What does this do to the carbon? What does this do to the carbon?
Does it reduce the dipole? No?
It changes. It changes
Yeah.
the dipole.
More positive.
You would think it might make it more positive, but it doesn't. And in fact does the opposite. And it makes the carbon more negative because now the magnesium is more positive. Okay? So a Grignard reagent creates this unique situation where you now have a carbon nucleophile. You now have a carbon nucleophile. When you react a Grignard reagent via mechanism, you are going to take the arrow from this bond here as if this is not even there. Okay? So this is synonymous with this. This is synonymous with this. Got it?
Isn't the magnesium ionically bonded to it would disassociate it?
It is going to disassociate, that's correct. That's actually how you get rid of it at the end, yeah, when you quench the reaction. You quench the reaction, you get rid of it. Iodine crystals are sometimes used as a catalyst in this reaction. I've seen that used, but you have to use very, very dry solvents in this reaction, okay? Why? So it doesn't disassociate and you don't quench your nucleophile before you even get started in the reaction. Does that make sense? Okay? So, Grignard reagents, these are strong and highly reactive. There are softer reagents than Grignard reagents, and we won't talk about these quite yet, okay? We can use copper in this mix along with lithium and make something called a cuprate, and it has different selectivity than a Grignard reagent. But we're gonna mainly just talk about Grignard at this point. How are we doing on time? Is that clock correct? Oh, we got a few minutes. Okay, say again?
Can manganese be used instead of magnesium?
I don't know if that's ever been done before. That's a really interesting thought. Okay? Okay. Grignard reagents attack ketones, aldehydes, and esters. And let's take a look at just doing a ketone. So, Grignard reagent and quench